On April 13th, 1970, 3 astronauts were 200,000 miles from Earth when a single miscalculation turned a routine moon mission into the most desperate survival story in human history. One catastrophic explosion, and 3 men suddenly stranded in the void of space with dwindling oxygen, failing power, and no clear way home. But here's what makes this story truly remarkable. It wasn't the mistake that defined NASA, it was what happened next. In this video, we're going to break down exactly what went wrong, why one math error set off a chain reaction of disaster, and how a team of engineers back on Earth pulled off what many called the greatest problem-solving feat ever attempted.
200,000 miles from Earth. 3 men are getting ready for bed. They've just finished a live television broadcast from inside their spacecraft, a tour of the vehicle that is supposed to carry them to the moon. Not a single major television network had bothered to air it. At Mission Control in Houston, Texas, a flight controller glances at his instruments and notices something odd, a pressure reading. Off by a fraction. Standard procedure, completely routine. He asks the crew to flip a switch. Jack Swigert flips the switch. Houston, we've had a problem. To understand how 3 men nearly died in space in April 1970, you first need to understand what the world looked like in the months before they left. Because the world had done something remarkable. It had grown bored of the moon. July 1969, Neil Armstrong becomes the first human being to walk on another world. 600 million people watched live. It is arguably the single greatest achievement in human history. 3 months later, Apollo 12 does it again. With precision that should be breathtaking, they land within walking distance of an unmanned probe that had been sitting on the lunar surface for 3 years, and America yawns. The Vietnam War was grinding, social unrest was boiling, and the space program, once the most watched show on Earth, was losing the plot war. Budgets were being slashed. Apollo missions 18, 19, and 20 were already being cancelled. The question being asked in Washington wasn't, how do we reach further into the cosmos? It was, can we afford to go back at all? Into this climate, on April 11th, 1970, 3 men climb into a rocket. Their mission, Apollo 13. The 7th crewed mission in the Apollo program, what would have been the 3rd lunar landing. Mission Control controllers would later describe the first 2 days of flight as boring. They were bored to tears. They would not be bored for much longer. Before we get to the explosion, I need to tell you about the 3 men inside that rocket and the 5-year chain of mistakes that put a time bomb in their spacecraft before they even left the ground. Jim Lovell was 42 years old, a naval aviator and test pilot who had already flown 3 space missions. He had orbited the moon on Apollo 8 in 1968, the first human beings to see its far side with their own eyes. He had been that close, and he wanted to walk on it. Apollo 13 was supposed to be his crowning moment, the mission that completed the journey. His wife Marilyn had reportedly thrown his wedding ring down the drain the morning of launch and never recovered it. Lovell, not a superstitious man, didn't take it as an omen. He should have. Then there was Fred Hayes, 36 years old, lunar module pilot, scheduled to walk on the moon alongside Lovell. Apollo 13 was his first spaceflight, and Jack Swigert, who also shouldn't have been there at all. The original command module pilot was a man named Ken Mattingly, meticulous, obsessive about systems knowledge. He had spent years learning every switch, every circuit, every procedure in the command module, arguably better than any other astronaut alive. And then, 6 days before launch, Backup crew member Charlie Duke's son came home from school with German measles. Duke caught the measles, exposed both the prime and backup crews during training. Of the 5 astronauts in both crews, only one had no immunity to measles: Ken Mattingly. NASA's flight surgeons made the call 72 hours before launch. 72 hours, Mattingly was pulled from the mission. He never got the measles, not a single symptom. His replacement, Jack Swigert, was a last-minute stand-in who had barely trained with the actual crew. In simulator runs, the 3 men proved they could work together. NASA approved the swap, and Mattingly, furious, grounded, and perfectly healthy, went to mission control to watch the launch. He would not stay a spectator for long. Here's the thing about that crew swap. It looked like the worst possible news for Apollo 13, but it was, unknowingly, one of the things that would save the crew's lives. I'll show you exactly how in a moment. But first, I need to take you back 5 years, because the real story of what killed Apollo 13 didn't start in space. It started in a factory, 1965, 5 years before Apollo 13. Engineers at North American Rockwell are redesigning the electrical systems of the Apollo Command and Service Module. The spacecraft normally operates at 28 volts of direct current, but the ground support equipment at Kennedy Space Center used for testing runs at 65 volts. So every component in the spacecraft needs to be able to handle both voltages.
Inside the service module, 2 tanks hold liquid oxygen, not just for the crew to breathe, but to feed the fuel cells that generate all of the spacecraft's electrical power and drinking water. Inside each tank is a small thermostat, a safety device. If temperatures inside the tank rise above 80 degrees Fahrenheit, the thermostat cuts power to the heater and stops it. Simple, essential. The thermostat is rated for 28 volts. Nobody tells the manufacturer about the voltage change. Nobody tests the thermostat at 65 volts. Nobody checks. The discrepancy sits quietly in the spacecraft, invisible, waiting. 1968, 3 years later. Oxygen tank number 2, the tank that will be installed in Apollo 13's service module, is removed from its original spacecraft, Apollo 10, for a routine modification. During the removal process, it is accidentally dropped. 2 inches. 2 inches onto a work platform. A fall so minor that on a human being it wouldn't leave a bruise. But inside the tank, something has shifted. The internal fill line, the tube used to drain the tank of liquid oxygen, is now damaged. The damage is internal, not visible from the outside. No one detects it. The tank is reinstalled, cleared for flight. March 1970, 2 weeks before Apollo 13 launches. Kennedy Space Center. The countdown demonstration test. Engineers fill the cryogenic tanks and run through pre-launch procedures. Standard, routine. But oxygen tank number 2 won't drain. The damaged fill line is blocking the flow. The tank simply will not empty through normal channels. Engineers write a discrepancy report. They discuss the anomaly, and they devise a workaround. Use the tank's internal heaters to boil off the remaining liquid oxygen. Run power to the heaters, convert the liquid to gas, and vent it out. It would take 8 hours. They approve the procedure and begin. Here is where the 2 mistakes collide. The heaters are powered by the 65-volt ground supply. The thermostats protecting those heaters are rated for 28 volts. As the temperature inside the tank climbs, the thermostat triggers. It should cut the power. It should protect the heater. Instead, at 65 volts, the thermostat simply welds shut. Fused. Stuck open. The heater keeps running. The temperature gauges inside the tank are only calibrated to read up to 80 degrees Fahrenheit. The technician monitoring the procedure watches the gauge. It reads fine. What he cannot see is what's happening inside. Over 8 hours, temperatures inside oxygen tank 2 reach an estimated 1,000 degrees Fahrenheit. 1,000 degrees. And Apollo 13 is cleared for launch. What no one knows, what no one can know without tearing the tank apart, is that on April 11th, 1970, when that Saturn V rocket leaves the ground, it is carrying a bomb in its service module. A bomb assembled over 5 years by 3 separate mistakes at 3 separate points in time. A voltage nobody upgraded in 1965. A 2-inch drop nobody noticed in 1968. 8 hours of invisible destruction, 2 weeks before launch. None of it was malice. None of it was incompetence in any simple sense. It was a chain, and every link looked harmless on its own. The explosion is 55 hours away, and there is one more thing you should know before it happens, because it makes what comes next almost unbearable to watch. April 13th, 1970, Monday evening. The crew has just finished a 49-minute live television broadcast, a guided tour of the spacecraft. Not a single major network aired it. But Mission Control, Capcom Joe Kerwin had told the crew earlier that the spacecraft was in good shape and that everyone in the control room was bored to tears. The crew were preparing to sleep. Then a flight controller noticed a slightly unusual pressure reading in one of the oxygen tanks. Standard procedure, completely routine. The third cryostir of the mission. He asked the Capcom to contact Swigert and have him start the fans. At 55 hours, 54 minutes and 53 seconds into the mission, Jack Swigert flipped the switch. Inside oxygen tank number 2, those bare, burned wires sparked. In a tank filled with pure liquid oxygen at negative 300 degrees Fahrenheit, the spark ignited the remnants of melted Teflon insulation on the fan motor. The fire superheated the oxygen. Pressure spiked. The tank burst. The crew heard a loud bang. The spacecraft shuddered. Warning lights lit the console. Swigert looked at his instruments and radioed Houston. "Okay, Houston, we've had a problem here." Mission Control asked him to repeat. Jim Lovell came on. "Houston, we've had a problem. We've had a main B bus undervolt." They didn't know what had happened. Not yet. 13 minutes later, Jim Lovell looked out the left window of the command module, and he saw it. Something was venting into space. A cloud of gas drifting silently outward into the void. It was oxygen, the lifeblood of the mission, the source of their power, their water, their air, bleeding out into nothing at a rate that couldn't be stopped. The explosion had destroyed oxygen tank number 2 completely. The blast had damaged tank number 1. Both were failing. The 3 fuel cells that generated all electrical power aboard the command module were shutting down one by one. They had, by NASA's calculation, approximately 15 minutes of power left in the command module. 15 minutes. The lunar landing was over. Now the only question was whether 3 men would make it home alive. Gene Kranz was 36 years old, a former Air Force fighter pilot. NASA's flight director, the man responsible for every human being in space during his shift. He had been in this room when 3 astronauts burned alive on a launch pad fire in 1967, the Apollo 1 disaster. He had watched what happened when NASA failed to anticipate catastrophe. He did not panic now. He pulled his team of engineers into a back room away from the main floor and told them something that became one of the defining sentences in the history of human spaceflight. When you leave this room, you will pass no uncertainty to our people. They must become believers if we are to succeed. Then he made his first critical decision. There were two ways to get the crew home. Fire the service module's main engine and come straight back, the fastest route. Or use the moon's gravity to slingshot the spacecraft around and back to Earth using the lunar module's smaller engine. The first option was faster, but the explosion might have damaged the main engine. Firing a potentially compromised engine with 3 men aboard could cause a secondary explosion, and there wasn't enough power left to run it anyway. Krantz chose the slower path, the long way home. The lunar module, Aquarius, was the crew's lifeboat, designed to support 2 men on the lunar surface for 2 days. They needed it to support 3 men for 4 days. The average age of the engineers in mission control was 26 years old. They ran on black coffee and cigarettes, and they were about to improvise in real time solutions to problems that had no manual. In the next 4 days, 3 separate things will try to kill this crew, and 3 separate times the people in that room will stop it. The first one comes within 24 hours, and it's not the cold, it's not the darkness, and it's not running out of oxygen. It's their own breath, carbon dioxide. 3 men in a spacecraft designed for 2, breathing in a cabin rated for 45 hours of life support. They're asking it to run for 90. The lunar module had cylindrical lithium hydroxide canisters to scrub carbon dioxide from the air. They were running out. The command module had more canisters, but they were square. The lunar module's slots were round. Within hours, carbon dioxide levels would reach toxic levels. The crew would suffocate, not from a lack of oxygen, but from breathing. Engineers on the ground, led by Ed Smiley from NASA's Crew Systems Division, had 24 hours to find a solution using only materials known to be aboard the spacecraft. What they had? Plastic cooling garment bags, cardboard from the cover of the flight manual, a spacesuit hose, duct tape, a bungee cord. They built a prototype on the ground. They radioed 17 steps of instructions up to the crew. Swigert built it in space. A square canister fitted to a round slot, sealed with duct tape, secured with a bungee cord, held together with a piece of cardboard from a flight manual. Carbon dioxide levels dropped to safe levels and stayed there. Duct tape and a plastic bag. That is what saved their lives. Meanwhile, back in Houston, Ken Mattingly was living inside a command module simulator. The problem? To survive re-entry, the crew would need to power the command module back up from a complete cold shutdown, something that was never meant to happen in flight. Writing the procedure normally takes 3 months. Mattingly had 3 days. He didn't sleep. He barely ate. He threw switch combinations for 72 hours, calculating the minimum power draw the command module could use and still reach Earth. Every watt mattered. One error in the sequence and the batteries would die before splashdown. On the evening of April 16th, he walked into mission control carrying a stack of papers, the power-up procedure. He sat down at the Capcom station, put on his headset, and spoke to his crew for the first time since the explosion. As the spacecraft approached Earth, Nobody knew if the explosion had cracked the command module's heat shield. A compromised heat shield means the spacecraft burns up on re-entry. The crew dies within miles of home. The heat shield held. And the reason it held was, indirectly, because of a tragedy 3 years earlier. After 3 astronauts burned on a launch pad in 1967, NASA had completely overhauled the command module's internal insulation. That same insulation prevented arcing when power returned to the frozen, condensation-soaked electronics. A disaster from 3 years before had quietly saved 3 lives in 1970. Re-entry into Earth's atmosphere creates a communications blackout. Plasma ionization, the heat of re-entry, blocks radio signals. It normally lasts 3 to 4 minutes. For Apollo 13, the blackout lasted 6 minutes. Nobody knew why. Mission Control sat in silence. 40 million Americans were watching live television. Across every time zone, hundreds of millions more watched around the world. For 6 minutes, the whole world waited. Then, a voice. April 17th, 1970, 1:07 p.m. Eastern Standard Time. Apollo 13 splashed down in the South Pacific Ocean, 3.5 miles from the USS Iwo Jima. 6 days after launch, 4 days after the explosion, 200,000 miles away from where they nearly died. The heat shield had held. The crew was alive. Gene Kranz wept. The engineers in Mission Control hugged each other, lit cigars, and cried. The entire Mission Control team was later awarded the Presidential Medal of Freedom. The first time in history the honor had been given to an organization rather than an individual. The Apollo 13 Review Board delivered its final report on June 15, 1970. Its conclusion wasn't a single failure. It was a chain, and every link in that chain looked minor in isolation. Apollo 13 is known officially at NASA as the successful failure. No one walked on the moon, and yet it demonstrated something arguably more extraordinary than a successful landing. It proved that when everything goes wrong, the most powerful computer on Earth is a room full of people who refuse to give up. If you made it to the end of this video, I want to know something. What do you think was the biggest mistake in this chain? The voltage oversight in 1965? The dropped tank in 1968? Or the moment someone looked at a stuck gauge in March 1970 and decided it was probably fine? Drop your answer in the comments. I read every single one. And make sure to subscribe to The Wired World.